Welcome back, students. In this video, we are going to look at the complete Sn1 mechanism, meaning all of the different things that can happen during an Sn mechanism that makes it more advanced than the simple one we've seen before. Let's start by revisiting the simple Sn1 mechanism. And when I say simple, I mean the simplest version of the Sn1 mechanism. In the simplest version of the Sn1 mechanism, what happens first is that your leaving group ends up leaving. Once your leaving group leaves, you form a carbocation, and once you have that carbocation, your nucleophile can attack. When that nucleophile attacks, if there happens to be a chirality center, you're going to get inversion and retention of configuration. Now, there's two main steps here. There's loss of leaving group and nucleophilic attack. And in the Sn1 mechanism, they're happening one after another. The leaving group is leaving first, then the nucleophile is attacking. So this is our two main steps that I'm going to refer to. The other things that can happen during the course of an Sn1 mechanism is you could have a proton transfer happen before those two main steps. In between those two main steps, you could have a carbocation rearrangement. And then after your two main steps, you could have a proton transfer, and you can also have a combination of these three options that I've listed here. What I want to do is go through an example of each of these possibilities. A proton transfer happening before the two main steps usually occurs when you have OH as your only potential leaving group. OH is a terrible leaving group. It's not going to leave. What you would need to do in order to get OH to leave is to protonate it first. So before the two main steps of the Sn1 mechanism even begin, that OH needs to be converted into a good leaving group. There's two ways to convert it into a good leaving group. We're going to focus on protonating in this example. The way that you protonate it is to add an acid. Sometimes you will see people write something like H3O+ in order to show that they've added acid, or sometimes people will write just HCl or HBr or something like that. Now, when we go through this protonation step, this pair of electrons is going to pull off a proton from your acid, and you're going to see now as your product, and it's not your final product, but it's just after the proton transfer, that now we have an ion here that this part that I'm highlighting in yellow looks a heck of a lot like water. That's an outstanding leaving group. Now what can happen is your leaving group can leave, and when your leaving group leaves, you have that carbocation form, and you have now water floating around in solution, and then your nucleophile can do the attacking to get your final product. And I'm just going to put in a general nucleophile here. We'll just do NuC, we'll make it negative, and we'll get our final product. So OH is a terrible leaving group. You have to convert it into something that will leave. Now, this idea of bound water, this part right here that I call bound water, has a fancy chemistry name, but I just call it bound water because you have enough fancy chemistry names to remember. So make sure that you are recognizing OH is awful. I know I keep saying that, but for some reason, I think because you're so used to seeing hydroxide in Gen Chem 2, that people don't really recognize at the beginning that OH cannot leave on its own. So this is a proton transfer beforehand. Let's look at the next possible addition to the Sn1 mechanism. Whenever you have an Sn1 mechanism, you always have to be on the lookout for a carbocation rearrangement. This is why we covered the potential carbocation rearrangements in an earlier video where we talked about carbocation stability and we practiced drawing rearrangements. Now we're going to utilize that during the course of mechanisms where even if you're not drawing the mechanism, even if you're just predicting a product, you still have to, in your head, pause and say, what carbocation does this form? Can it rearrange? And it's going to take a lot of practice to get there. Let's look at this. The first thing that's going to happen is your chlorine is your leaving group, and that is going to leave. When the chlorine leaves, you end up with this carbocation. Now you have to pause, you have to look at it and say, can this rearrange to form a more stable carbocation? And the answer is yes. Remember that what we do is we find the carbon that bears the positive charge. We look at the carbons next door, those are called our beta carbons. And we ask ourselves, if the positive charge was on one of those beta carbons, would it be more stable? And for this one, the answer is no, it would not be more stable. Going from a secondary to a primary, that's like water flowing uphill. It's not going to happen. But if we were able to get the positive charge over onto the left-hand side, where I'm going to draw an arrow and point to, then that would be allylic. Let's just draw what that would look like really quick, and then we'll draw the arrows. So if we know we want to get the positive charge to here, I just want to remind you how this is pi bond, one atom away, positive charge, right? That's allylic, which means it's in resonance. So a secondary carbocation, which is what this one is, to a secondary allylic, that is going to rearrange. You can't stop it from rearranging. The question is, how are you going to draw the rearrangement? What you need to do in this case is when you have a hydride shift, in these skeletal notations, you don't have the hydrogen drawn that's going to shift, so you need to draw in that hydrogen. The location where you want the positive charge to end up is the place that a shift is starting from. You have a hydrogen here, and that hydrogen is going to take its electrons and move to the carbon next door. Remember when we talked about carbocation rearrangements, only atoms that are beta to the alpha carbocation can shift, and there's no hopping, right? It's not like we're playing leapfrog over here. You can only shift immediately adjacent to where the carbocation is currently located. And your hydrogen plus your electrons shifts over to where that carbon with the positive charge is. When it shifts over to that carbon with the positive charge, we can draw it in. We can put it here just as a visual reminder of where it went. Now that location has filled its hole, right? It had a hole. That's what a positive charge is. It's a lack of electrons. Now that location has a hydrogen plus its electrons, so it has 4 bonds. And what happened is where we shifted from now has a hole. And that's why the positive charge is where it is. I'm going to highlight in yellow. That's going to turn that green in your subsequent structure. Now that you have a positive charge that is the most stable representation of what's going to happen in this reaction, then your nucleophile can attack. Your nucleophile here that will attack is the CH3OH, and what will happen is the OH, the O, is your nucleophilic atom, and it is going to come in and attack that carbon. I'm not going to draw the subsequent product because we wouldn't finish due to the fact that this actually folds in our last idea of having a proton transfer at the end. So let's segue really quick into some more discussion about carbocations, and then we'll hit that last idea about proton transfer at the end. I just want to do a quick reminder about carbocation stability so that you don't feel lost when we talk about carbocation rearrangements. Remember, that's what's happening in a carbocation rearrangement is you are looking at a structure and you are asking yourself, can this rearrange? Does this have the capability of forming a more stable carbocation? And if the answer is yes, it's going to happen. We're just trying to mimic what happens on paper. So first of all, we need to remember that carbocation stability increases when we look at how substituted a carbocation is. What we're doing is we're comparing the carbon that has the positive charge, and we're looking at how many R groups are attached to that carbon with the positive charge. The more R groups that are present, the more stable. The reason is called hyperconjugation. Hyperconjugation is the fancy chemistry word for saying those R groups have a situation going on where their orbitals are aligning in such a way that they can donate a little bit of electron density to that empty p orbital. And if that empty p orbital feels less empty because it has a little bit of electron density from neighboring groups, that is what gives rise to stability. Another thing that gives rise to stability is resonance. So don't forget about allylic, like we saw on the previous page, and benzylic carbocations. These are going to be quite stable because they participate in resonance. One of the pitfalls that we run into as students is looking at alkyl halides and thinking that these alkyl halides are going to react because we think they're forming allylic and benzylic carbocations, and they're not. Our brain is tricking us. So what I want to do is I want to show you what vinylic looks like. So here is vinylic, and what's happening with your brain, and it's tricking you, is when that iodine leaves, you actually get a positive charge on the carbon that's sp2 hybridized. This is not a stable carbocation. This is not going to form. The way that this tricks your brain is when the iodine is still attached, it makes you think that the positive charge can be at the end of the bond where the iodine is, and it tricks you into thinking that when the iodine leaves, it's actually going to form something that it's allylic. But remember that the iodine plus its electrons, so the iodine and its bond, are going away. So the place that the hole is going to be is on this carbon that I just highlighted in yellow. So you need to start getting your brain to recognize the difference between vinylic and allylic. The same type of thing happens with aryl alkyl halides and benzylic alkyl halides. If we look at this one where the iodine is directly attached to the ring, when that iodine leaves, it actually makes a positive charge on one of the sp2 hybridized carbons. This is not stable. This is not going to form. Again, what's happening in your brain is your brain is seeing that iodine and it's seeing that bond, and it's just taking away the I to make you think that it's actually going to form a benzylic carbocation, and it's not, because when that iodine leaves, the iodine plus its electrons leave, and what happens is you get a positive charge on the carbon on the ring. So you also want to make sure that you're not letting your brain get tricked into thinking that aryl alkyl halides are actually going to be benzylic carbocations. So these are the two things that I think give people a lot of trouble in this area. I want to end our discussion with looking at proton transfers after the reaction of the two main steps for Sn1 mechanisms. After those two main steps, if you have a neutral nucleophile, you're going to see a proton transfer at the end. Let's draw those first two main steps. The iodide is your leaving group, and it is going to leave. When that leaves, you then have a carbocation, and your water is going to be not only your solvent, but also your nucleophile. When you have your water be your solvent and your nucleophile, that has a special name. It's called a Solvolysis reaction. One more time, a Solvolysis reaction is when your solvent is your nucleophile. Sometimes it can make us feel like something's missing because we don't have a solvent and a nucleophile, but in actuality, they're one and the same. Now that we have that carbocation, our nucleophile is going to attack. I'm just going to redraw the water here, which is the nucleophile, and I'm going to add my electrons to the oxygen so that I'm indicating that my arrow tail is starting at a pair of electrons. Then I'm going to draw my water attached. So now I have my water here, and your water still has those two hydrogens on it, which means that it now has a positive charge on that oxygen. This is where we're going to end up with a proton transfer at the end. Now here's the key. What's going to pull off that proton? This is what's tricky, is figuring out what's going to pull off the proton. You got two things in the reaction flask. One thing that you have is the iodide, and the other thing that you have is water. And you might pause and think, hello, didn't we just use the water? Nope, it doesn't work that way. Because when you have a little bit of water, you have lots of water. 1 liter of water contains 55 moles of water molecules. So when you even have a drop of water, you have boatloads of water molecules. So we're not looking at like a balanced chemical reaction here. When you have water, trust me, you've got plenty of water. And those are your two entities, right? Water and iodide. And you're going to look at this, and your natural instinct is going to be to use the iodide, and it's not correct. Don't do that. Because iodide is the conjugate base of a very strong acid. So if our two options to pull off the proton are water and iodide ion, I think that the natural instinct to use iodide ion comes from the fact that just you're used to seeing iodide in Gen Chem 2. But in actuality, if we look at the base strength of these, water is the stronger base. So water's going to end up pulling off the proton here and doing that proton transfer. Now, I will warn you that sometimes some textbooks do it wrong. And I think that they do it wrong because they're tired, right? They're tired of repeating themselves and trying to get students to remember their Gen Chem 2 stuff. But I'm young and I'm not tired. So you need to make sure that you know that it's water that pulls off the proton. Let's talk about it in one more aspect. Iodide cannot pull off the proton, because if iodide were to pull off the proton, you would recreate HI, which is one of the 7 strong acids, or 6 depending upon your Gen Chem 2 teacher, that you learned in Gen Chem 2, right? It is one of the strongest acids that you are aware of. A weak base cannot pull off a proton to make one of the strongest acids you're aware of. That's not possible. Again, that would be like water flowing uphill. That's like you putting a ball at the bottom of a ramp and going, ball, roll up the ramp. It's not gonna happen. So just get used to pausing and thinking, what is going to pull off this proton? What do I have in the flask? What is my strongest base? There's a reason that we spent so much time on pKa earlier on in the semester. Let's wrap up. In this video, we looked at Sn1 reactions more thoroughly. We reminded ourselves that these reactions are stepwise, and that the first thing that happens is you lose a leaving group, and then the second thing, a nucleophile attacks. There were 3 additional steps that can happen, and it's not just that one of those additional steps can happen per reaction. You could technically have any combination of these additional steps occur. You want to be on the lookout for carbocation rearrangements every single time you see an Sn1 mechanism, and then if your nucleophile is neutral, you're going to have a proton transfer at the end. And if you have OH as your only potential leaving group, you're going to need a proton transfer at the beginning. Thanks so much for watching. I'll see you in the next video. This is Katoni, signing out.